All right, good morning, everybody. Happy Math Day. Sorry, I'm at JV Tennis Region. But the good thing is, you're going to learn day one. I'll do a few examples, you'll have a few practice. But there's a day two, we'll go over it again. So when I come back on Tuesday, we'll hit this again and you can ask lots of questions. But pay attention to these few examples, and you're going to try a few because you still are going to have some practice today that you're going to do in class. And hopefully not have homework if you use your time wisely. So, to begin, we're going to review what we did last class. Last class we learned, by the way, I'm on page 31. So turn there. Last class we learned about the rational root theorem. It's very helpful to give us all the possible roots that could happen, and then we can check them with the remainder theorem. So let's start with that. What are the possible rational roots? So if you look at this, the first thing that you gotta do when finding the list of possible rational roots is identify your p, identify your q, because remember the list is every factor of p divided by every factor of q. So my factors of p are 1, 2, 4, and 8. Don't worry about the negatives. Remember, we'll take care of those at the end. And then the things that multiply to give me 3 are 1 and 3. So for my possible list, I'm going to take every p and divide it by every q. So 1 divided by 1 is 1. 1 divided by 3 is 1/3. 2, 2/3. Right? 4, 4/3. 8, and 8/3. Got a little excited about the 8/3. And remember, for every positive possibility, there's a negative as well. So some people just do plus or minus instead of in front of each one instead of rewriting the list. Totally up to you. Okay, there's our list. So then our next job would be to check it on the remainder theorem, either by hand or on our calculator, but I just wanted to review how to get that possible list. So today, we are going to factor these. We're going to see what's going on and find the roots. And not all of them will be rational today. So we're going to find every single root, maybe irrational, imaginary. We're going to find, in this case, all three. Okay, so that's our goal. So I have a list of things that you're going to do here. The very, very, very first thing that you're going to do is check if there's a GCF. There's not an A, so I'm going to skip that step. And then 2, use the rational root theorem to come up with your possible list. So our our Q is 1 and our P is 30. So the factors of 30 are 1 times 30, 2 times 15, 3 times 10, 4, nope, 5 times 6, and that's it. The nice thing is they're all divided by 1, so all I need now is the negatives, or are the negatives. And I have my complete list. These are the possibilities, right? And they're not all going to work, but those are the possibilities. So, if you're doing this by hand without a calculator, you're just going to plug all of those numbers in for x and see which ones actually work, okay? So, just take 1, plug it in for x, see if you get 0. If you get 0, it's a root because the remainder would be 0. You plug in a 2 in for every x. If you get a remainder of 0, it works, okay? So I'm going to go ahead and go to my calculator, though, because that's a lot of numbers to plug in. So I would rather just check it, make the calculator do all the work. So I have to type in the original function, if you remember, into y equals, so that the calculator has that function to plug in the things. So I hit graph, and I can see my 3 roots. So I can see 1, 2, 3. They might be irrational though, so if the numbers don't work, I'll check that out. But I noticed that 1 is negative and 2 are positive, so I'm going to first try to identify that negative one. So it looks, I'm going to try negative 5, and it works. So negative 5 is a 0, okay? All right, now I'm going to try 2, and it is also a 0. And then I'm going to try 3. And it is also a 0. So I have negative 5, 2. So out of this list, negative 5, where are you, negative 5? 2 and 3 were the 3 roots. So this is where we kind of stopped last class because we're like, okay, we found our roots, woo. But Her roots are 2, 3, and negative 5. What we're going to do today is, we're going to say these are the solutions. But we're also going to change it to factored form, just so we can kind of review that and see what's going on, and we'll need it later. So we're going to go from our roots to our factors. And remember, when you go to your factor, it's like this. You're saying x equals negative 5, and we bring it back with the x. So if you remember, it has a sign change. So if you were to multiply these three things together, you would get that, okay? Which I just asked for the solutions, but we're going to do this just to help us see it all lined up, see what's going on. Like I said, it'll help you a little bit more later on. Okay, another example. So I am looking for 3 solutions again. My P has a few less factors than the other one, and our Q's 1. That's so nice, right? Okay, so rational root theorem. We got to find the possible solutions here. So we aren't not plugging in just a million numbers into the calculator, plugging them in. Gives us a condensed list, right? So every factor of P divided by every factor of Q. So for my list, I'm going to have 1 divided by 1, 3 divided by 1, and negative 1, negative 3. So only 4, hopefully 3 work. So we're going to go ahead and plug that into our calculator, or plug in each number by hand to check the remainder theorem. So y equals x cubed plus 3x squared plus x plus 3, and graph. Oh no. As you can see, there's only one solution, okay? Which is okay. That's why I'm here, to teach you what to do when you can only find one using the method. All right, so I'm going to trace and make sure that it is indeed negative 3, and it is, because as you see, the output is 0, which means the remainder would be 0. Okay, so I know that x equals negative 3, but I need 3 solutions because the degree is 3. So if the calculator, so remember, this is the list of possible rational. So there might be imaginary, there might be irrational, but in this case I'm pretty sure that they're imaginary because I didn't see them hitting the x-axis. So what you have to do when it is probably imaginary or irrational is you're going to take the factor, the root, that you do know about, and change it into a factor. So I just add 3 to both sides, I get x plus 3. So what we're going to do is we're going to divide x plus 3 out, so get it out of that function, x cubed plus 3x squared plus x plus 3. We're going to get it out and see what's left over and see if we can find our solution there. So we are going to do box method division to divide it out, which, good thing we've already practiced that, and you'll feel super good about it, right? So I'm going to undo the multiplication. So I'm going to think, all right, what's x cubed divided by x? Well, that's x squared. But then I need to multiply it because it didn't go perfectly. So I line up x squared and 3, and I get 3x squared, which is really nice because, as you can see, I have x cubed, I have 3x squared. I'm on to a good start. So I'm going to bring down my x now. Okay, what's x divided by x? 1. And then 1 times 3 is 3. No remainder. So I have everything accounted for, and I know that x plus 3 times x squared plus 1 is the factored form of the original. Okay? So through division, I can factor, just like you did last year. And then you just use the zero product property once it's in factored form, and you get all solutions. And remember, square root of negative 1 is I. So negative 3 is a solution, I is a solution, negative I is a solution. And you've just factored a complicated polynomial and found the solutions. Good work. All right, so we are going to go to your homework right now, we're going to do number 2 together, unless I might do another one. But I want you to cross off 6. I feel like 6 is a little bit too time consuming. So everybody cross off 6, 7, and 8 are review. So don't forget to do 5, 1, 3, and 4. But I'm going to do 2 with you. All right, so first off, we need to recognize how many solutions we're going to find. And hopefully you've recognized we got to find 3 solutions, okay? So we're going to do the rational root theorem. Here's my p, here's my q. Factors of p are 1, 4, and 2. Factors of q are 1 and 2. So I'm going to take every p and divide it by every q. So 1 and 1/2. And then 4 divided by 1, 4 divided by 2. Then 2 divided by 1 is 2, which I already have, and 2 divided by 2 is 1, which I already have. So I have those 4 numbers with also their negative. Okay? All right, so I'm going to check that list on the calculator. So I'm really using the remainder theorem, but I don't like to do it by hand because it's time consuming. Okay, so 2x cubed minus 25x squared plus 20x minus 4, and check that out. Okay, so it looks like I have a solution there, but it's happening twice because as you can see it bounces off the x-axis. So let's test it. It looks like it's pretty small. We know it's not negative, so I'm going to test negative 1/2. Oh, that did not work, right? Okay, trace, let's test 1. That did not work. Trace, where is it? Let's test 2, did not work. And let's look at our list again. All right. Okay, so 1, 1/2, negative 1/2, negative 4, negative 2, right? Okay, so let's make sure I typed it in right. 2x cubed minus 25x squared plus 20x minus 4. All right, so graph that sucker. Let's see. Trace 1/2. Oh, 1/2 works. Maybe I typed it in wrong or didn't remember to check it. All right, 1/2 it is. So let's see. We know we have 3 solutions. One of them is 1/2. It kind of looks like it's happening twice. We'll check that out. But we know that we need 2 more solutions because the fundamental theorem of algebra says that we need 3 because the degree is 3. So remember, take the solution you know about, get it into factored form. Okay. Now, let me show you a trick. If you don't like working with fractions, we can multiply it by 2, because when I distribute the 2 and I'll get 2x, and then 2 times 1/2, half of 2 is 1. So I just want to show you real quick. It's a trick that you can use. You just, whatever the denominator is in your factor, you just multiply by that. Because remember, we know the solution is 1/2. So if I take 2x minus 1, set it equal to 0, I can get 1/2 that way. So it's an equivalent way to write it, and it just helps some people that don't like to work with fractions. But if you're fine working with fractions, go for it. All right, so we have to divide 2x minus 1 into our beautiful function up there. So here's 2x cubed. So 2x cubed divided by 2x gives me x squared, which gives me negative x squared when I multiply it down there. But notice I needed negative 25x. So negative 1, I need negative 24x squared more to get negative 25x squared. And then 2 divided by negative 24 divided by 2 is negative 12x, which will give me positive 12x, which means I need 8 more there. Right? So 12 plus 8 is the 20x, and that's positive. I accidentally made a mark, so I don't want to think it's negative. All right, and then 8 divided by 2 is 4. So that gives me negative 4, no remainder, and of course there's no remainder because we already knew it was a solution. But this helps us know that 2x minus 1 is a factor along with x squared minus 12x plus 4. All right, so if we use the zero product property, we can solve. Remember this one on the left, we already know is 1/2, but I'm going to do it anyways. So zero product property, 1/2. Now 2 of the solutions are here. So I'm going to see if I can factor. I'm going to think of the things that multiply to give, because if I set up the zero product property, I'm not going to be able to solve. So I'm going to think what multiplies to give me 4, adds to give me 12. So I have 1 times 4, negative 1 times negative 4, negative 2 times negative 2, 2 times 2. None of those add up to give me negative 12. So on a couple of these, you're going to have to factor, and if you can't factor, you're going to have to complete the square, or if you use the quadratic formula, you can use that as well. So I'm going to complete the square. So the 4 is causing issues, right? The 4, we can't solve it with that 4. We can't factor it. So I'm going to get the 4 out of the way. And then, if you remember, I'm going to do another box method thing because we really are kind of just dividing. I'm going to put x squared here. And then I'm going to half negative 12, which gives me negative 6x, negative 6x. So I have x squared minus 12x, which will put an x here, an x here, a negative 6 here, negative 6 here. So we've factored the new one, but remember, we need our, so negative 6 and negative 6, we need our square completed. So we're going to need a 36 here. All right. But you can't just go around putting 36 into equations. So I need a positive 36 here. All right, we got to balance it out. If you put 36 on each side, you're balanced. So I'm going to continue to factor this, but I already did the work here. So the factor is x minus 6 squared, and then 36 minus 4 is 32. Now I can solve. So to get the left-hand side alone, I got to get rid of the square. So I'm going to square root. I'm left with x minus 6 equals plus or minus the square root of 32. I'm going to add 6 to both sides. X equals 6 plus or minus the square root of 32. So there are my other two solutions. 6 plus the square root of 32, 6 minus the square root of 32. So if you still have your notes from before, we went over completing the square earlier because you're going to need it this year, like I said. You're going to need factoring. But that's what we do. So if you turn back to page 32, you're going to see the instructions. Check if there's anything that can be factored out of every term, GCF. If there's a number that divides evenly into each coefficient, take it out. Does every term have an x on it? Take it out. Use the rational root theorem, the remainder theorem, write it in its factors, and solve for the unknown. So we did a few examples, one with all rational roots we could just get from the calculator, some with imaginary. The imaginary were really a little bit easier to find because we were just able to solve when we got it to factored form. And then we did an example here, number 2, where we had irrational. All right, well, good job, guys. If you have any questions, save them for Tuesday or work together, but try the rest of these examples, 1, 3, 4, 5, and then 7 and 8. All right, have fun.